Okay, so this morning we will be discussing ions. The very first thing we're going to discuss is the trend in the size of an ion. After that, we're actually going to start talking about the individual ions and how to name whether they're monoatomic ions or whether they're polyatomic ions. So that is the plan for this morning. So ion size. Yesterday, I introduced the concept of ion, looking at the electron configuration and how the electron configuration changes with the formation of an ion. And in introducing the concept of these changes in the electron configurations, we said that cations result from the loss of electrons and anions result from the gain of electrons. Now, one thing that I did not introduce when we were talking about those electron configurations of the ions is something called an isoelectronic series. Basically, an isoelectronic series is a series of atoms or ions that have the same number of electrons and hence will have the same electron configuration. With respect to ion size, I'm mainly going to focus on the isoelectronic series, simply because it is going to be the one that is the most straightforward. To be quite blunt, it is the one that is the most straightforward. So before I get into the description of the ion size and how I want to just use your imagination. We're going to describe the parental, the family. And we're going to describe, when we describe the family of a family, we're going to describe the protons as your parental unit, and then the electrons as the individuals, the children of the family unit. Now, let's say I have a family that has 3 children. What happens to the size of that family unit if one of those children go off to college or go off to the military or go off, basically leave the family unit, leave the household? What happens to the family unit if a child leaves the household regarding its size? The size gets smaller. Guess what happens to an atom when its electron, its child, leaves the atom. It's going to get smaller too. So what we can say is that a cation is going to be smaller than a neutral atom. Because basically it lost an electron. It lost that electron left home. And so the size got smaller. Now, let's talk about the other option. And that is we have our family unit and we bring in more kids. What happens to the size of the family? It gets larger. Well, that's the same thing that happens when we bring in electrons. We're bringing in more kids into the atom, and therefore it's going to get larger. So a neutral atom is going to be smaller than an anion. Now, with this cation, now let's take this one step further and let's talk about each addition or subtraction. So we have our neutral atom. We've already said if it loses a kid, it loses an electron, it's going to get smaller. So a +1 is going to be smaller than a neutral atom. What if it loses 2 kids? It loses 2 electrons. What do you expect to happen to this little bitty family called an atom? If it loses 2 kids? Becomes even smaller. So a +2 is smaller than a +1. And as might be expected, a +3 is even smaller. Now the other direction, if we only add 1 kid, it grows a little bit. But if we add 2 kids, it's going to grow more. And if we add 3 kids, it's going to grow even more. Folks, what we just described by using this idea of an atom being a family unit and the electrons being kids that have either come into the household or has left the household is the trend in ion size. This is your ion size trend for an isoelectronic series. That's all there is to it. So if I were to say put those in order of decreasing size, meaning biggest to smallest. First of all, you need to know that those are isoelectronic. Sodium plus has 10 electrons. Fluorine minus has 10 electrons. N3 minus has 10 electrons. Mg2 plus has 10 electrons. And Al3 plus has 10 electrons. So they are isoelectronic. So when we talk about putting these in order of decreasing size, that means since they're isoelectronic, I want the biggest of these first. So that means my N3 minus is going to be listed first. It's going to be bigger than my F minus, which is going to be bigger than my Na plus, which is going to be bigger than my magnesium 2 plus, which is going to be bigger than aluminum 3 plus. Any questions about the trend in ion size? Okay, the question I just received, is this only when they're isoelectronic? Yes. Unfortunately, there are other variables that have to be taken into account, such as atomic size, when we start getting them mixed up all over the periodic table. And so it becomes more challenging to actually sort through the ion size unless they're isoelectronic. So on an exam, you'll only be asked about an isoelectronic series. Okay. So now, this is actually a great segue. We are going to start talking today about compounds. Up to this point, what we have focused our attention on is the atom of the element. We know that all atoms of elements known to man are found on the periodic table. We know that we can look at the periodic table and determine the number of protons in a neutral atom of an element and the number of electrons in a neutral atom of an element, all by looking at the atomic size. All by looking at the atomic number, excuse me. We have described where all of those subatomic particles reside. The protons, which are responsible for an element's identity, reside in the nucleus. The neutrons, which are responsible for the isotope of an element, reside in the nucleus. And the electrons, which are responsible for an element's reactivity, reside in the electron cloud. We then have spent time describing that electron cloud. Excuse me. And learning how to determine the address for every single electron in the atom of an element. That address is described by the electron configuration and the associated quantum numbers. We talked about some of the various properties that can be determined using the electron configuration, such as being able to recognize whether something is in its ground state or if it's in its excited state, whether it is paramagnetic or diamagnetic. And then we started talking about the valence electrons. The valence electrons themselves are the ones that are responsible for the element's reactivity. And so we talked about how to take these valence electrons, and in the case of cations, they lose valence electrons to make positively charged ions. In the case of anions, the elements gain electrons to make negatively charged ions. And we talked about the electron configuration for those ions. Today, what we're going to do is we're going to talk about these ions in greater detail. And we're going to talk first about monoatomic ions, which is essentially the ions that we have been focusing our attention on up to this point. And then we're going to talk about polyatomic ions. Okay, so with respect to your monoatomic ions, mono means one, atomic atom, ion. There are three categories of monoatomic ions. The first category of monoatomic ions are going to be cations of elements that always form the same charge. The second category are going to be cations whose charge varies depending upon the anion they are associated with. And the last type of monoatomic ion that we're going to be talking about are anions of nonmetals and metalloids. Okay. Key points. With respect to your cations, again, these will be metals. So you have to know that division that we talked about. Is it a metal or is it a non-metal metalloid? Because if it's a cation, it's going to be a metal. Whereas, again, as I've already mentioned here, the monoatomic anions will be your nonmetals and metalloids. Okay. I think it was today I put into your folder this document. This document shows the monoatomic cations whose charge is always the same. So that first category that I listed in the previous section or the previous slides. And it also lists the monoatomic anions, which are your metals, which are your nonmetals and some of your metalloids. What it does not list is it doesn't list the monoatomic cations whose charge varies depending upon the anion they are associated with. So let me explain how to read your periodic table. If you look at the metals in group 1, you will note that they are all a +1 charge. That is because your group 1 metals always form a +1 charge if they're part of an ionic compound. Your group 2 metals always form a +2 charge if they're part of an ionic compound. Then you have to skip over to what I refer to as the stair step, which I've highlighted in blue, which includes silver, zinc and cadmium, aluminum, gallium, and indium. These 6 metals also have a constant charge when they are part of an ionic compound. With silver, it always forms a +1 charge when it is part of an ionic compound. With zinc and cadmium, they always form a +2 charge when they are part of an ionic compound. And with aluminum, gallium, and indium, they always form a +3 charge when they are part of an ionic compound. Now, the reason I call this my stair step is because, number one, it looks like a set of steps. But I also like to refer to this as a stair step because it will help you to memorize the charge that these elements take on when they are part of an ionic compound. You will notice that silver is the only element in its step. One element plus one charge. You will notice that zinc and cadmium are the two elements in the next step. Two elements plus two charge. And you will notice that the aluminum, gallium, and indium are three elements in the third step. Three elements plus three charge. So by knowing that the stair step begins at silver and drawing it, you can also predict the charge that those elements have. And for some reason, I am unable to see my chat. Let me pull it up on my other one. Hold on. In case you have questions. Okay. Now, those group 1 metals, group 2 metals, and the stair step, those are the ones that always form that particular charge when they make an ionic compound. Those are the metals that always form the same charge when they are part of an ionic compound. And I emphasize metals. The rest of the metals, which are not listed on this periodic table, the rest of the metals form charges that vary depending upon the anion they are associated with. The next thing I want us to look at is the anions, which are your nonmetals and metalloids. You will notice that if you have a nonmetal or metalloid in group 15, they always form a -3 charge if they're part of an ionic compound. Your group 16 nonmetals and metalloids always form a -2 charge if they are part of an ionic compound. And your group 17 nonmetals always form a -1 charge if they're part of an ionic compound. The ones listed on this periodic table, again, are the elements that always form the constant charge. Their charge never changes. It's always the same charge. Okay. So metals that form a constant charge. Again, that is group 1, which will be a +1. Group 2, which will be a +2. Silver, which will be a +1. Zinc and cadmium, which will be a +2. And aluminum, gallium, and indium, which will be a +3. To name these, you name the metal, followed by the word ion. Basically, folks, you won't have to use the word ion all the time, but if it's all by its little lonesome, you want to use the word ion so that you're distinguishing it from the neutral atom. So that's why on that particular periodic table, I said sodium ion, because I wanted to distinguish sodium ion, which is Na+, from sodium metal, which is just Na. I want to distinguish magnesium ion, which is Mg2+, from magnesium metal, which is just Mg. So again, that word ion came into play simply to distinguish it between the neutral atom and the positively charged cation. Now with group 2, or with the second category, which is the metals whose charge can vary depending upon the anion. With these, it's like yesterday, I gave you iron. Well, iron can form iron 2+, or it can form iron 3+. Gold can form gold 1+, or it can form gold 3+. If you look at the periodic table that I posted that I just showed you, you would see that iron and gold are in the metals that aren't listed. That's because they have charges that can vary. Now, let's talk about how to name them. To name these metals, it is insufficient to simply call it by the element name followed by the word ion, because I need to know what charge they have. So it is important to list the charge as part of the name. To distinguish which ion is present. This is accomplished by listing the charge as a Roman numeral in parentheses following the name of the element. So just as a reminder, if there is one, or if the charge, if it's a +1, in other words, it's going to be, we're going to use the Roman numeral 1. If it's a +2, we're going to use the Roman numeral for 2. If it's a +3, we're going to use the Roman numeral for 3. If it's a +4, the Roman numeral for 4. 5 will be the Roman numeral for 5. 6 will be the Roman numeral for 6. And 7 will be the Roman numeral for 7. I don't believe there is a +8 out there, or 9 or 10. And the reason is, if you'll recall yesterday when I was talking about ionization energies, keep in mind that those ionization energies occur in a stepwise fashion, and each one adds up. And we saw real quickly that with magnesium, it went from 737 for the first loss of an electron to 1400 for the second loss of electron to 7700 for the third loss of an electron. Each of those added, all of those are added up, and therefore to make a +3 charge takes a lot of energy. To make a +7 charge is going to take a lot of energy. So we don't have a whole lot of atoms that will make a +7. We don't have a whole lot of atoms that will make a +6, but they do exist. And that is supposed to be a V for that 5. It changed it on me. There we go. Maybe it won't change it now. So anyhow, that is the reason most of them will be a 1, 2, or 3. We don't get into the 4, 5, 6, 7 that often, but there are a few out there. So let's just go back to iron 2+ and iron 3+. If I name iron, then iron 2+, it's going to be iron 2, so that I can distinguish it from iron 3. And gold 1 is going to be different than gold 3. And that is to distinguish, that is to take the metals whose charge is dependent upon the anion that they're associated with, and it is to help distinguish which version of that metal cation I have. Questions about metal cations as a whole, whether it's the monoatomic cations whose charges is always the same, or whether it's the monoatomic cations whose charge varies. Are there questions about how we name those ions? Is there a question about who those ions are? Because you have to be ready to distinguish. Are you talking about a monoatomic ion whose charge is constant? Or are you talking about a monoatomic cation whose charge varies? You've got to be prepared to distinguish those among those categories so that you know how to name them. Before I go on to the anions, I do want to go back and do one thing, and that is I need you to go back up here to the where I started the monoatomic ion discussion. And I want you to write that that is the, basically, this is the start of test 3. Okay, now let's talk about your monoatomic anions. And again, even though it's on the other sheet, we're talking about nonmetals and metalloids only. For the charges, if it's group 15, it'll be a -3 charge. If it's group 16, it'll be a -2 charge. And if it's group 17, it'll be a -1 charge. Now to talk about the names. When you name a monoatomic anion, basically the name is going to be the root of the element, followed by the ending IDE. You're going to hear me emphasize this IDE because anytime, with very few exceptions, if it ends in IDE, it means that it is an anion of an element. Okay, so let's look at, so N3-, that we're talking nitrogen, so this becomes nitride with the IDE ending. P3- is phosphorus, so this becomes phosphide. As3 minus is arsenic, so this is arsenide. For group 16, O2 minus is oxide. S2 minus is sulfide. Se2 minus is selenide. And Te2 minus is telluride. Then with group 17, F minus is fluoride. And folks, I think I emphasized this once before, but I can't remember in this class. It is fluor, like in a fleur-de-lis fleur. It's not flour-eyed, as in the stuff you use to make dough. It's fluoride. Cl minus is chloride. Br minus is bromide. I minus is iodide. And At minus is acetatide. So again, the IDE is important. IDE is indicative of the anion of an element with very few exceptions. Okay. There is a third document in your folder that lists out a lot of the ions. And I am going to share this screen now as soon as I can find my Zoom again. And it is simply called ions. Now, do you need to memorize all of these ions? The answer is no. You do need to know the first several from lithium down to cadmium. Because those are the metals whose charges are always the same. Those are your group 1, which are +1. Your group 2, which is +2. Your silver, which is a +1. Zinc and cadmium, which is a +2. And aluminum, gallium, and indium, which are +3. You have to know those. The next batch of ions, starting with scandium and going down through bismuth, you do not need to know. You need to know how to name them, but it's not going to do you any good to memorize them. And the reason it's not going to do you any good to memorize them is because I haven't listed out all of the anions of an element whose charges vary. I listed a small portion of them. So therefore, you don't even have all of them here to memorize them. I will come back to ammonium and the hydronium. The others, though, that you do need to have down are your anions of your nonmetals and metalloids. That's your group 15, 16, and 17 elements. Group 15 forms a -3, group 16 forms a -2, group 17 forms a -1. And all of the anions of the elements end in IDE. Now, starting with, well, technically ammonium and hydronium, and really starting with borate and going on to page 2, you get into your polyatomic ions. And yes, you must know your polyatomic ions. You must have them memorized, or you must know how to get to them, one of the two. I am going to discuss the relationships among your polyatomic ions today. But some students just find it easier to go ahead and memorize their polyatomic ions. It is up to you which way you want to go. But you are going to have to know your polyatomic ions. And you're going to have to know this entire list plus the ammonium, hydronium, and borate from the previous page. Now, whether that means, now I have posted a Quizlet that will allow you to flip through these, but it may be that you are more of a tactile person and need to make your own flashcards. Whatever you got to do, you got to do. Let me get it where I can see if y'all have comments. Okay. So in the folder that I posted today, this is the other document that you'll see. And I am going to make it larger. And hopefully it'll work for you. Okay. There are some, in this document, there are some notes to help you. For example, in period 2, you will notice that all of them that end in ATE have 3 oxygens. So borate if I say borate, it means it's a that first, let's start with number one. If you see ATE or ITE, it means it's a polyatomic ion. Again, if you see ATE or ITE, it means that it is a polyatomic ion. Specifically, if you see ATE or ITE, it's a polyatomic ion of that element and oxygen. Again, if you see ATE or ITE, it's a polyatomic ion of that element and oxygen. So when I hear borate, ATE, I know that it is a polyatomic ion of boron and oxygen. When I hear carbonate, ATE, I know that it is going to be a polyatomic ion of carbon and oxygen. Nitrate is going to be a polyatomic ion of nitrogen and oxygen. Now the question is, how many oxygens? And that's where it helps to know what period the non-oxygen element is in. If the non-oxygen element is in period 2, it is always going to have 3 oxygens. So borate is BO3, carbonate is CO3, nitrate is NO3. Now ignore group 17 at this point, because group 17 is unique. Group 17 is unique, but for the most part, if it ends in ATE and it's in period 2, it's got 3 oxygens. The other thing you will notice is that borate has a -3 charge, carbonate has a -2 charge, and nitrate a -1 charge. In other words, the charge is steadily going down as you go from left to right. So what I guess I'm trying to say is, if you can remember borate, you have a lot of information about carbonate and nitrate as well, because borate has 3 oxygens and a -3 charge. Carbonate will have 3 oxygens and a -2 charge. Nitrate will have 3 oxygens and a -1 charge. Now, when you move, when you move to period 3 through 7, things become even more interesting as far as some similarities that you can draw upon. First of all, the 8s. In period 3 on, the 8s will have 4 oxygens. So period 2, the 8s had 3 oxygens. Period 3 on has 4 oxygens. The other thing that's really cool about period 3 on is that the charge on the polyatomic ion is going to be the same as the charge on the elemental ion. So for example, sulfide, IDE, because it's in group 16, has a -2 charge. Sulfate, because it is going to have a -2 charge as well. Again, this only starts at period 3. It's not valid for period 2. Period 2 is the oddball here. But starting at period 3, this works. Now, group 15 and group 16 are known as families of 2, meaning they have one polyatomic ion that ends in ATE and one polyatomic ion that ends in ITE. The ATE and the ITE are identical except for the number of oxygens. The ATE is going to have one more oxygen than the ITE. So let me repeat that. Group 15 and group 16 are known as the family of 2, meaning there will be an ATE and there will be an ITE. The ATE will have one more oxygen than does the ITE, but everything else remains the same. Now, group 17 is known as a family of 4 when it comes to the polyatomic ions. If you look at the polyatomic ions, you will notice that they go down. Look at the 8s and the ites, the ATEs and the ITEs. If you look at the ATEs and the ITEs, you will notice that basically those 4 polyatomic ions differ by 1 oxygen each. So we go from ClO4 to ClO3 to ClO2 to ClO1. All we're doing is dropping off an oxygen each time we go. But the rest of it remains the same, meaning the charge is the same and it is connected to the oxygens. The only thing that changes is the number of oxygens. Now, no 2 ions can have the exact same name. Because no 2 ions can have the exact same name, we cannot use just 8 and ite. We have to use something else along with the ATE and the ITE. And that's something else that we use is a prefix for the largest of the polyatomics and for the smallest of the polyatomic ions in group 17. A neat thing that you will notice is that 4 oxygens with a -1 charge gets the prefix per. That is true, period. If you have 4 oxygens and a -1 charge, put that prefix per to it, because that's going to be true. So there's one polyatomic ion that I haven't given you that's MnO4-. Because it has 4 oxygens and a -1 charge, it's going to get that prefix per too. And then the smallest of the family of 4 gets the hypo. Now, the other thing that let's see, it's 10:31. So what I would rather do instead of getting into this any further is I would rather wait until Tuesday to continue this conversation, let you digest some of what has been stated today, so that when we can build upon it on Tuesday when we're back in person, when I think I can make I can do more with you than I can do today on Zoom. So with that, I am going to say, number one, all of this is on Blackboard. Number two, I will stay on to answer any questions you may have until 10:40. And number three, I will be back between noon and 2 using the link that I sent out yesterday for office hours if you would like to attend. And number four, you have all of the information you need to be able to do the homework that is due on Tuesday, which is related to the topics we discussed this week up through ion sizes. And with that, I am done for the day. Have a good weekend. Yes, there is a quiz today. It's over last week's material, I believe. Whatever the homework is over, it's over the same thing. The homework that was due on Tuesday. It's over the same thing. Have a good day and stay warm.